Hello everyone. In this session, let's have a quick overview of the decision trees. So here we would talk about what is a decision tree, why are decision trees really are needed in data analysis, for what purposes we use the decision trees, the advantages and disadvantages associated with the decision trees, and what is the typical mechanism behind the working of the decision tree on a broad scale. Of course, there are different kinds of algorithms for different decision trees, but there are some things which are common. So, we will try to understand what is the basic logic behind the working of the decision trees. Here, let me tell you, in this session, I'll not be using any tool or technique like R. We are primarily trying to understand the conceptual aspects behind the decision trees. When you are building a model based on decision trees, what are some of the important points that you have to keep in mind? That is what we are going to discuss here. How do I really prune a decision tree? Right? If the tree is so long, if the tree has so many branches, if the tree has so many leaf nodes, how do I really cut it short? That is what we are calling as pruning the decision tree. What is that we have to keep in mind if we have to prune the decision tree? Then, for the improvisation purposes, we use some procedures called cross validation. We will be discussing about that, very heavily used in the decision tree mechanism. Cross validation. There are again a couple of methods of doing this cross validation. So we will be talking about those mechanisms as well. Whereas when we take up data sets from the next session onwards, we will be doing them on the data sets. We will be doing cross validation on the data sets. But here, because this is a conceptual session, we'll try to understand why do we really need to do the cross validation and how do we do the cross validation. Then, what if the data that I have considered has a few missing values? How do I handle that? And finally, I would also talk about some of the places where you need to be cautious when you are working with the decision trees. Some of the most commonly made mistakes and where you need to be very careful regarding the usage of decision trees. First important point, the decision trees are applied to both regression as well as the classification problem. When I say a problem is a regression problem, I'm trying to predict a numerical variable. That is a regression problem. I want to estimate the value of a numerical variable. That is what is a regression problem. And when I am saying classification problem, I am trying to estimate a class to which this particular data belongs to. So my estimation is typically a categorical variable. So wherever I want to estimate a categorical variable like, okay, group 1, group 2, whether this particular object belongs to high performance or low performance, whether this particular person will belong to default or no default kind of category. So in those cases, we are calling them as classification problem. Whereas when my intention is to predict a numerical variable, I want to predict the price of a particular product, then it is a regression problem. Now the trees can very well be used, the decision tree approach can very well be used both to regression problem as well as classification problem. Some of the good things about the trees, the result that you get out of these trees, it's in a simple and easy to understand format. So few things, there are no statistics involved. I don't need any kind of knowledge in statistics to understand and interpret the decision trees. So generally the output of the decision trees are presented in pure English form. I mean any person who can have a logical way of understanding a decision tree can present the results of the tree in simple, easy to understand English. So it selects an outcome by building a tree. It creates different possible decisions, right? At every stage, different possible decisions are created, and based on that, a tree structure is created like this. And based on this, the output is typically selected. So at the nodes, at the what are called as the leaf nodes, the last of those kind of nodes, the outcome is typically selected. So that's how the tree models typically work. And they are non-parametric, means they do not assume the data to follow some kind of a distribution. We know for some kind of statistical methods, they assume that the data that we are using, it follows a normal distribution or it follows a Poisson distribution, some such kind of stuff. Whereas in the case of decision trees, we see that they are majorly non-parametric. They do not make any kind of assumptions regarding the distribution of the data, and inductive learning. The whole learning is happening based on the reasoning. So if you have to explain things to someone, it's much easier to explain when you have built your model using decision trees compared to the same kind of objective being accomplished through some other complex models like neural networks, support vector machines, etc. So that way the explainability of the model is more and more simpler when it comes to the decision trees. Then they produce classifiers for a given problem. So the whole problem is typically classified, and using this kind of a classification model, I should be able to do the prediction for new and unseen situations. So for the new data, new input data, I can very well apply the model and try to find out what would be the outcome for that kind of a data, right? So it could clearly give me two things. Once a model is built, I can use that model on the new data and try to do the predictions. That's one thing that I can do using the decision trees. Then the second thing is I could also try to identify what are the mechanisms that are driving a problem. So if I want to try to predict, if I am in the process of understanding the default behavior of people on loans, I would like to see, given the characteristics of a new loan applicant, I should be able to assess whether he would be defaulting on the loan or he would not be. And at the same time, I want to try to understand what are the various factors that are typically driving the default. So any of these things could come into picture when we are talking of decision trees. In practice, we generally construct a tree, and the leaves, these are what we are calling as the leaves. So in the leaf, we are getting a particular class attribute, especially when we are talking about a classification tree. So each of these leaf attribute, we will get a class. So this is default. This is no default. This is default. Whereas this default is actually the rules for this particular default are these different criteria. So if a person is falling into all these criteria, then we can say that he can default. Whereas if a person is falling into this criteria, then he may not default. So that's how the whole tree is getting built. And the inner nodes. So these are all the inner nodes. They represent the descriptive attribute. Salary greater than something, age less than something. So these are the different descriptive attributes that are typically being represented. At each internal node in the tree, a single attribute value is compared with a single threshold value. Age is one attribute. Age less than or equal to 40. Salary greater than 20k. So that's how each single attribute is compared with single threshold at each of the levels. So at this node there is one comparison. At this node there is one comparison. So at every node there is one comparison. So based on that you'll get a binary kind of stuff. Either my data will fall towards this child node or towards this child node, and based on that comparison the data will be falling into this or this kind of a node. And when the leaf node is reached, means when there is no more possibility of a bifurcation, then for this particular leaf node a class is typically assigned. Is it going to be a default category or a non-default category? So that's the kind of a class assignment that is typically done. So that is what goes into a decision trees. Right, in this session just look at the basic conceptual overview of the entire process. Obviously getting into more and more details of it, we will take up different data sets, try to work out on them to give you more and more inputs into the practical aspects of the usage of the decision trees for different purposes. Now, some of the positives, we will also look at some of the negatives, but majorly the positives. We have already highlighted some of them. They are very easy to understand. The rules are very clear. So I don't need to be a statistician to understand the rules. My domain knowledge is sufficient enough to understand the different rules that are used for the selection of a particular class or for doing some kind of prediction of a numerical value. The rules that are typically being used, they are self-explanatory to the domain experts, and I can very well track and evaluate every step in the decision making process. The whole tree, I should be the whole path, I should be able to track it, see which one is coming, which rule is first being applied, followed by which rule, and so on. And there are a set of attributes which are the variables that are influencing the class. So they are the ones. So I'll be able to identify which set of attributes are really playing a major role in doing the differentiation across the classes, in distinguishing across the classes. Now, here some important points are the attributes, especially the variables that are used as explanatory variables, right? The variable that we are trying to predict, we are calling it as a response variable. The variables which are used as drivers for prediction of this response variable are typically called as explanatory variables. Now, or sometimes we call them as input attributes. So all of them are interchangeably used. Now those input attributes can either be nominal, means they could be categorical data, they need not be numeric all the times. They can very well be categorical variables, or they could be numerical variables. So there is really no hard and fast rule that they all need to be numeric, which means the flexibility is much more when we are using decision trees. They are capable of handling data sets even if they are misclassified values. Missing values are there. See, some models, what happen is if the data has a lot of missing values, the model will simply break. The model will not go forward. Whereas with respect to the decision trees, we don't have such kind of problems. Even if there are missing values, the data is very well handled, the model is very well built. So they can be easily programmed for use in real-time systems. So even the computational cost, right? We don't need high powerful systems for creating the decision trees. So compared to various other models used for similar purposes like neural networks, support vector machines, these decision trees are computably inexpensive. And I can use them quite comfortably even on large data sets or even on very small data sets as well. They work quite comfortably both on large data as well as smaller data. And as I have been telling you, they are non-parametric. So they really do not make any kind of assumptions regarding the distribution of the variables. No, they don't need. We don't need to have the data to be normally distributed or Poisson distributed or any such kind of statistical distribution. So that's where we are calling them as non-parametric. So you could find there are lots and lots of advantages that are associated with the decision trees. But on the downside, they run into a big risk of overfitting because there is a possibility that a particular pattern may not be significant at all, completely insignificant kind of a pattern, and that even the learning will happen on that pattern also for the classification purpose. So the reading will happen to such an extent that instead of generalizing the behavior, almost all the specific behaviors will be studied. And because of that, what could happen is this is a specific behavior of a particular set of data. See, some person who has a very high salary, who has been prompt in paying the loans every year, there's a very limited chance that he will default. But there was one person, let's say, who has defaulted. Now the model will try to read that specific things about that particular person, and whenever similar kind of a person comes up in the future, it will give me a result that he will default. Whereas in reality, 99% of the cases, such kind of people may not default at all. This is called overfitting. We are trying to learn so much from the data that we are not able to differentiate between generalization and specification, specific behavior, and unnecessarily make mistakes during the classification of the result. So they might well work with the original data, the data with which we have typically built the tree, but their accuracy levels will be much poorer when we are executing the same tree on the new data. So it is suggested that when we are working with decision trees, we should consider this concept of pruning. Don't try to build the tree to a very big length. Don't build a very long tree with 10 different layers. Try to cut off the tree after a few layers, 3, 4 layers. Try to cut the tree, and that could very well limit the risk of overfitting. It will result in smaller decision tree. The size of the tree is very small. Only a very few important attributes that are influencing the tree will be considered. All other attributes which have a very negligible influence on the outcome, they would typically be ignored when you are doing the pruning process. Now that we know that decision trees are advantageous, we'll see what is the typical fundamental that goes behind the working of the decision trees. There are so many algorithms, right? In the next few sessions, we are going to discuss each of these algorithms itself. But a few things that I would like to highlight here is the general principles behind the working of the decision tree. They are very much similar, right? Probably it's like if I take algorithm 1 and algorithm 2, probably 60% is more and more similar between these two algorithms. Only the 40% is more and more specific to each one of them, right? The specifics are differing across the algorithms, but general principles behind the building of the tree is more or less common. So here, terminology wise, we use something called learning set, where we know the classified states. So when I'm saying classified states, default, no default, right? Or win, tie, or loss. So these are the examples with known classified states. So these are the three classified states here. These are the two classified states here. So we have a learning set. Then we use the word parameters. We are talking about a set of test attributes. So which are the variables, which are the factors that will decide whether a person will default or he will not default, whether a particular team will win or lose or tie. What are the set of attributes that are going to decide this final classified state? Those are all coming out as parameters. So the process is, it starts at the root node. This is the root node at the top of the tree. So here the whole sample, let's say we have taken a sample of 500 observations. So the entire sample of examples are typically used at the beginning, and this is typically getting split like this. This whole process, it gets split, right? So the goal is to split this whole set of examples into subsets where the classification purity is higher. When I say classification purity, now when it comes here, it should sure happen that almost all the elements in this particular class, let's say this 500, based on some rule, this side it became 200, this side it became 300. Another, on this 200, another rule is applied, making it 50 here and 150 here. And here another rule is applied, making it 40 and 10. And it should so happen that out of this 40, if all 40 of them belong to one single class, win or loss, no issues at all, then that is where we are calling it as highly pure. But even if that is not the case, the percentage should be much higher, right? If not 100%, even 80% of them are wins and 20% are losses. And I may not, I can't split the data even more further. Then this is what is a measure of my purity. There are different measures of purity. Entropy and information gain are some of the very commonly used measures of purity. But let's try to understand that the goal of any decision tree is increase the purity of classification. So whatever the splitting that is happening, if every partition is pure, means all the examples in the partition, they belong to the same class, then no more further bifurcation happens. the decision tree for that particular partition is typically stored. And there is a labeling that is done for each node with the name of the class. So that leaf node will be marked as no default or default, win or loss or tie. And if that particular group is not pure, then you will think of further doing some kind of partitions on that particular node. But if that node has come out to be pure, then you don't want to do any kind of partitions based on that particular rule. So that's how recursively the whole splitting process happens, to such an extent that based on different attributes I should be able to split the tree, and in the process of splitting the tree I should be able to improvise the purity levels. So stop when all the newly created nodes are terminal ones and they contain pure enough. When I'm saying pure enough, to a large extent they should belong to one of the groups. Now this is where the different models will differ. How the data is split, which attributes are used for splitting the data, right? Which one is used first, which one is used next. What is, on what basis the splitting of the data in based on the rules is typically happening. When to stop splitting. Again, different algorithms have different mechanisms on when to stop the splitting process. How they prune the trees, right? When should the structure of the tree be cut down, and in what way the structure needs to be cut down. So different algorithms that are typically getting developed in this field, they vary in all these aspects. So they use different variants of impurity measures. So I can use information gain, which is purely based on the concept of entropy. They use something like Gini index, the gain ratio, the distance based measures. Different algorithms use different kinds of mechanisms. So this is what is the mathematical part. But of course, because we are using a tool like R to solve all these kinds of problems, we hardly have any kind of issues. The syntax typically gives provisions for all these kinds of splitting measures, assessing measures, etc. So we really don't need to spend too much of a time in terms of understanding the mathematics behind each of these modes. Now, a few important points that we really need to understand when we look at the decision trees is, whenever we are trying to validate the decision tree, how good it is, we look at two important calculations. One being the sensitivity, to what extent it is able to identify the positive result. So let's say, let me build a small grid, right? No default, default, no default, default, right? And this is what is their predicted result, and this is what is the actual result. So let's say out of the 500 observations, right, I'm just putting some numbers: 300, 100, 25, 75, right? Let's say some numbers I'm putting for this 500, and for me the positive is default, right? Because I want to know which person is going to default. So I will take the positive as default, and no default I'll take it as a negative. Now, to what extent it is able to identify the positive results. So this is what is my prediction of positive results. And specific ability is to what extent it's able to identify the negative result. So the sensitivity typically is measured as number of true positives. So the true positives are 100, because I have predicted as default, actually also they were default. So the number of true positives are 100 and number of true negatives, these are the true negatives, right? So this is what is coming out as the sensitivity. So number of true positives divided by number of true positives multiplied by number of true negatives. Percentage of cases correctly classified as belonging to class A among all the observations known to belong to class A. And similarly, so when you are saying true negative, sorry, of belonging to class A, okay, so actually belonging to class A there are 175. I think there is some problem with the formula here. So actually there are 175 that are belonging to the default category, but my system is able to identify only 100 of them. So the sensitivity comes out as 100 divided by 175. Whereas when it comes to specificity, percentage of cases correctly classified as belonging to class B among all the observations known to belong to class B. So there are 325 observations that are belonging to class B, out of which 300 of them are identified correctly. So 300 out of 325 happens to be the specificity. And overall, when I'm talking about accuracy, I'm taking 300 plus 100. They are correctly classified out of the overall 500. So the overall accuracy is 80%. This is the sensitivity. This is the specificity. Now generally what we do is we set some kind of thresholds for both sensitivity as well as specificity and try to change the model to see which model is able to meet our sensitivity as well as the specificity measures. So here this is typically used for classification purposes. So from the statistical performance measures perspective, these are not statistical performance measures like log likelihood, mean squared errors, etc. So this is purely the classification and misclassification rates. So all the possible algorithms will be typically tried out and we are going to check which one is going to be best fitting the data, and whichever one is going to be best fitting for that data we would be using for the prediction purposes as well. But of course we have to be cautious about the overfitting that might be very much possible in the process. Now, why do we really need to prune the decision tree? Right? Why can't we keep it by default itself? Try to understand two things. If the tree is too small, only one layer, right? Only this much. So what could happen? There is only one rule, right? So based on this rule, my data would be classified either here or here. So this would be the leaf node. So this might be default, this might be no default, which means there is only one single variable that is influencing the default versus the non-default. So there is a possibility of misclassification of the important characteristics. There could be various other attributes that are impacting the default, but here it's only one single attribute that is considered. Means a lot of other attributes which could influence your decision variable, they are typically getting ignored. Whereas if I make the tree too big, there is a possibility of a large amount, a lot of overfitting that is done on the data towards a particular one specific element. So the pruning is very important, especially when you are building one single tree, right? One single tree with one data set. Let's say I have a 500 data Out of this, I called 350 as my training data and 150 as my testing data. I build a model with this 350. I test it on this 150 before I roll it out to the new data altogether. But if I build one single tree, then it's better that I have to do a pruning. But nowadays, the pruning is not that much required because we have a concept of random forests wherein there are multiple trees that are built, not just one single tree of 350, 150. There are multiple trees of 350, 150 that are built. So multiple decisions are going to come out and the actual decision is taken based on the voting process. Right? Which of these different trees, how many out of these different trees that are typically built, how many of them are suggesting that this person will default and how many of them are suggesting that this person will not default. So when we are using random forest, we really don't need to bother too much about the pruning of the decision tree. But when we are trying to build a standalone individual decision trees, then pruning also plays a very important role. Then another important concept that we really need to understand when we are doing the decision trees is the process of cross validation. So whatever the model that we have built, right, we are testing it out and the whole testing process or training a model building process is based on reasoning and logic. Now we have to look at how good, we want to assess how good is this typical model. Now for that people have different mechanisms. One is called as leave one out cross validation. Means if I have a sample of 100 observations, I will leave one out. Means 99 of them will be there as a part of my training data. One would be there as a part of my testing data. Take out one observation from the sample and train the model with the rest. So if my sample is 100, I'll take 99, call it as my training data and test it with this one. So trained predictor is applied to the excluded observation. So I'll try to build a model with this 99 and I'll test it on this one single observation. Then this one is added back to the sample, another one is brought out. So like this whole process continues 100 times. So here the first one is excluded, remaining 99 are included. Then the second one is excluded, remaining 99 are included in the training model. So like that, this test is performed 100 times for all the observation. So based on these 100 results, right, in each of these 100 situations, we are going to get which classification, right, for a particular data, which class is more and more appropriate. And based on that, the model assessment is typically being done. So that kind of assessment is typically called as leave one out cross validation. This is very, very appropriate, especially when you have a very small sample size. But if your sample size is decently large, we have another mechanism called n-fold cross validation. So your samples of 100, I'll split them into groups n-fold. So let's say 10-fold. So means each group will have 10 elements. Each group will, so the whole 100 is broken down into groups of 10 each. So these are typically used to prevent the overfitting of the model. I divide the training set into n subsets of equal size. This is what I have done. Sequentially, one subset is tested using the classifier train. So now I'll use these 90 to build the model and test it on these 10. After that, I will call this as my test set and I'll build the model with the remaining 90. After that, this will become the test set and the model will be built with the remaining 90. So each of these different models, so there are different models that are getting built, and in each model we are testing a different set of data altogether. So each instance of the whole training data is predicted once, and all observations are used for the training purpose n times, whereas from testing purpose they are used once. And accuracy is measured as the percentage of the data that is correctly classified. So that way the model is much more effective. So generally, if I have to make my model more and more effective, we can think of one of these two methods. Either I can do a leave one out classification, or I could go with an n-fold cross-validation model so that the overall model can very well be improvised. So when we are applying them on our data, you will get a much more better clarity regarding the cross-validation process. Now, in some cases, there is a possibility that the data that we have collected may have some missing values. Generally, majority of these tree models, they ignore the misclassified data point, especially when they are going with an evaluation of the split. When I have to decide to which group a particular data needs to be put. So if a particular value is missing, that particular point will not be considered for evaluation of the split. But once the splitting is done, the that particular observation is either assigned to this class or this class. Means it would not be used to build the rule, but once the rule is built and the child nodes are identified, the missing valued records are sent either here or here, again based on the various aspects. So depending on the largest number of instances, so if this group has 300 and if this group has 200, all the misclassified ones are all the missing valued records, they will be pushed to this particular group. So that could be one process. Or distribute to all child nodes with diminished weights. So probably distribute it in the proportion of 60% of the missing values here, 40% of the missing values here. Rather than distributing all the missing values to this particular group, there could be a possibility of distributing 60% of them here, 40% here. Or there could be a complete random. So there is no logic behind which one would be selected to which particular group. It's a random. Or create surrogate attribute. This is one more thing that is possible with some algorithms. They create surrogate attributes which closely resemble the test attributes. So we try to create, okay, which ones is it very closely resembling. So which record is very closer to this particular record, and directly use the values of that particular record, send the misclassified values to that particular group. So there are different ways in which missing values are typically handled in the data. Right, again different algorithms, they have different process to handle this missing values if they are present as a part of the data. And few important things, the generally believed maxim is if I have more data, I would be able to perform better analysis. But let me tell you, that could add even the complexity to the model. The reality is I should be able to reduce the number of attributes used for building the decision tree to the minimum set, but each of those variables should be highest value adding kind of attribute. So identify, it's not the quantity that matters. Even if you have a very few attributes, they should be very highly powerfully contributing to your decision variables. So the tree size and complexity depends on the size of the training set. If your training set is too large, there is a good possibility that the tree size will be much higher, the model will become more and more complex. So any information that any attributes which are nowhere informative, better try removing them off before the construction of the tree itself, right? Domain wise, if you understand this particular attribute may not contribute at all to my response variable, what I suggest is better remove it in the beginning itself before the construction of the tree only. There is a good chance that the model will become more and more complex the more the number of attributes you are adding to that model, right? So some of the important points that you have to keep in mind while building your decision tree model. So this is what I wanted to take up as a part of this session. From the next sessions onwards, anyhow, we are going to deal with different kinds of decision trees, where I would look at a decision tree if my response variable, if my response variable is categorical with more than two categories, categorical with only two categories, binary. I could also look at numerical. Response variable is a complete numeric variable, or in some cases it could be a count variable, or it could be an ordinal variable like low, medium, high. So some such kind of ordinal variable, or it could be a time to event kind of variables. So all these things are different kinds of sessions that I am going to look at using the different functions and packages in R. We'll take different data sets for each of these purposes, which can help us in trying to understand the model more and more effectively. If you have any more further queries regarding this particular session, you can very well get in touch with me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.